triple integral is, of course, going to have three integral signs. We're going to have some region that we're integrating over. The function is going to be a function of x, y, and z. And instead of putting a dA here, I'm going to put a dV. All right? dA represented a small little piece of area. dV represents a small little piece of volume. All right? Now, dV we will think of as like a little tiny little infinitesimally small cube. Well, maybe not a cube, but a box. It doesn't have to have equal dimensions. And the dimensions of this box, it'll have a dimension in the x direction, that'll be dx. It'll have a dimension in the y direction, that's dy. And it'll have a dimension in the z direction, that's dz. So it makes sense to view dv as dx, dy, dz. Because if I multiply this dimension times this dimension times this dimension, the width times the length times the height, I get the volume of the box. And so that should, these infinitesimal widths multiplied together should give me the infinitesimal volume. So when we did the dA, we saw that we could write it as dx dy or dy dx. Well, dV, you can mix these up as well. And you could write it dx dy dz. You could do dx dz dy. You could do, let's put the dx in the middle. You could do dy dx dz. Right? There are 6 possible ways to arrange these dx, dy, and dz's. Right? So whereas for the double integral, we only had 2 ways to think about it, dx dy or dy dx. Here we're going to have 6 different ways we have to think about arranging our triple integral. Now, in a lot of cases, there's going to be more than one way that works, so it's not like you have to hunt through all of these to find it, but there are all these possibilities that we will have to keep in mind. All right. I want to start with an example. Okay. So this is our function of x, y, and z, right? It's just xz plus y. And I want to integrate this function over the simplest possible thing, just a box. Okay, let's start with something very nice and simple. Where R is the box defined by it's a set of points, x, y, z, such that, okay, now I'm going to give ranges for x, y, and z. So x is going to be between -1 and 1. Y is going to be between 0 and 2. And z is going to be between -1 and 2. Okay. Usually they'd write this in a list. They wouldn't stack these on top of each other. So you have a comma and these would be listed out. But just to save space, I'm just writing one on top of the other one. So I'll put commas here. All right, so that defines a box. So what I'm going to do is I'm going to go to CalcPlot 3D. So you should be seeing a picture of a 3-dimensional box. Okay. So I've set it up in CalcPlot 3D, just kind of show you what we're dealing with. So you can see that x goes from -1 to 1. Right? On the x-axis, this box goes from -1 to 1. Y goes from 0 to 2. If I look on the y-axis there, it's going from 0 to 2. And the z is going from -1 to 2. So by specifying those intervals, I'm specifying a box here. So we have some function, our function xz plus y is defined at each point in this box. So take any point in this box, I get a value of my function. Now I can't sketch for you a graph of this function because if you look at the domain here, it's 3-dimensional. the graph assigns a value to each one of those points in that domain. So that's a fourth dimension. So to graph this, you'd need to graph it in 4 dimensions. I mean, there are tricks to kind of getting a way to visualize something in 4 dimensions, but I think it's best just to rely on our mathematical knowledge to understand what we're doing. So I can't really draw the graph for you of the function, but knowing what we know from the 2-dimensional case, we can kind of extrapolate what will have to happen here. So that was our region R. Okay, so when I set up a triple integral over a box, it doesn't matter what order I do these in. If these are all constants, it's not going to matter. I could do any one of these 6 orders, and they'll all work. So let's just set it up where we do, let's do dx, dy, dz, okay? So what I'm thinking of is that for each fixed z, I'm going to integrate with respect to x and y. And for that integral, for each fixed y and z, I'm going to integrate with respect to x. So I'm thinking about what x ranges from. Well, x goes from -1 to 1. Y goes from 0 to 2. And z goes from -1 to 2. So first integral is the x integral. Okay, so I'm going to treat z and y as if they're constants, and I'm just going to find the antiderivative of this with respect to x. Well, that's going to be, what, 1/2 x squared z plus, y is a constant, so I just get yx. Right, so this is going to be, I'm leaving those outer 2 integrals alone, but I've found the antiderivative for the innermost integral. Now I have to evaluate this. This is the antiderivative of this. I'm going to evaluate this from -1 to 1. And then I'm going to integrate that dy dz. If I plug in 1, I get 1/2 z plus y. All right, so let me just save space, I'm just going to write this down over here. I'm going to get 1/2 z plus y when I plug in 1. And when I plug in -1, I'm going to get 1/2 z minus y. And so when I subtract those, the 1/2 z's cancel, but I get y minus -y, I get 2y. So this whole thing just becomes 2y. Okay, so there we go. 2y. Oh, that's dy first, and then dz. Okay, so the next step, we're going to antidifferentiate 2y with respect to y. Well, the antiderivative of 2y is y squared. So I'm going to evaluate y squared from 0 to 2. And then I'm going to integrate that with respect to z. Well, let's do that on the side over here too. Y squared evaluated at 2 is 4. Evaluated at 0 is 0. So that's just 4. So this really is just the integral from -1 to 2 of 4 dz. Antiderivative is for z. Evaluate that from 2 to -1. So I'll just go this way. Evaluate that from -1 to 2. And let's see, that's, if I plug in 2, I get 8. If I plug in -1, I get -4. And so the answer is 12. Okay, like I said, you could do this one in any order. So you could try it dz dy dx or dy dz dx or something like that. You'll get the same answer every time. Let me just sketch the region that we were dealing with here. We said that x went from -1 to 1. So I guess my region went from here to here. Y went from 0 to 2. So I had, on the base, I had this rectangle here, and then z went from -1 to 2. So it's kind of like that's the region that we're dealing with, all right? So we went up to 2 here. As low as -1 on the z-axis. So when we set up the integral like this, what we're doing when we're working our way towards the innermost integral, we're thinking of fixing a z. For each z, you're doing an integral with respect to dx dy. So you could think of that as an area integral. So for each fixed z, I'm actually finding the area I'm integrating over this area within my box. This plane that intersects the z-axis at that number. And when I do that area, what I'm doing is that for each fixed y, I'm integrating with respect to x. So for every y in that area, so if I fix a y value in here, I'm going to integrate in the x direction. So kind of rewinding it that way is a way to think about it. I fix a z, and that prescribes for me a kind of a sheet, which is a little area. And then within that area, now we just think about it like we were thinking about the integrals in the section involving double integrals. For each y in that area, I'm integrating along an interval in x, right? So you can think about breaking it down in that way. And so we're kind of breaking it down from working from the outside to the inside. And thinking about it that way is going to help us deal with integrals over regions that are a little bit more general. So for instance, what I want to do is I want to look at a region that's not a box. I want to look at, let me pull up CalcPlot 3D here. So here we have a region that's almost a box, but look at the top. The top is not flat, right? Well, it's at an angle anyway. And so we want to integrate over this thing for the next problem. But I want to keep in mind what this region is defined by. The y values are just ranging between 1 and 2. The x values are ranging between 0 and 2. But the z values are not ranging between two fixed numbers. They're going from 0, but they're going up to something that depends on x and y. Now, the surface that I defined here, you can actually look down and how I define this. Z is actually equal to x plus y. So that's what defines this slanted surface that's at the top. Okay? So for this particular problem, we're going to do this triple integral over a region. The function I'm going to do is just x. All right? So R is given by the set of points x, y, z, such that, let's see, y was between 1 and 2. X was between 0 and 2. Let's start with x. Y was between 1 and 2. And z, now, z goes from 0, but goes up to not a fixed number. It depends on where we are with respect to x, y. It goes up to the plane x plus y. And so a way to think about that, kind of how we were thinking about that other picture up above. So x is going from 0 to 2, y is going from 1 to 2. And so we have this rectangle in the xy plane. If I fix an x, then I can position myself anywhere along this line inside that region, right? By specifying a y. And then I've specified an x and a y. So for each x and y, I can now specify how much my z has to go up. So my z is going to go from 0 to x plus y. So my z is going to go up to x plus y. And that's going to change depending on what my x and y values are. So I get this kind of slanted surface. I don't remember exactly how it was slanting, but I get some slanted surface up there. All right. So for each fixed x, I did a y, and then for each x and y, I did the z. So when we're thinking about this integral, what we're doing is we're doing the x on the outside, and then the y, and then the z. You work your way outside in like this. The x's were ranging between 0 and 2. So the outermost integral is going to have 0 to 2. Now for each one of those x's, y is going from 1 to 2. So y is going to go from 1 to 2. And then once I've specified x and y, I know that z is going from 0 up to here, x plus y. It doesn't make sense for me to specify this until I've already specified where I am with respect to x and y. Otherwise, z doesn't know what value this is, right? So until I've done the x and y integrals, it doesn't make sense to put this x plus y piece up here. Otherwise, z doesn't know how high to go, right? So you got to keep that in mind so you make sure you get things in the right order. You'll also notice that these variables will never be the same as this one here. And then this variable will never have a z or an x in it for kind of the same reasons. And these will always just be numbers on the outermost integral. All right, so let's unwind this integral and see what we get. So first we're going to find the antiderivative with respect to z. All right, so we're going to go, well, that'll become xz. And then we're going to evaluate that from 0 to x plus y. All right, well, if I plug in x plus y in place of z, I get x squared plus xy, right? And when I plug in 0, I get 0, so I don't have to subtract anything here. So I get this. Now I'm going to anti-differentiate with respect to y. So I get x squared y plus 1/2 xy squared, and I'm going to evaluate that from 1 to 2. Well, let's see. When I plug in 2 for y, I get, let's do that over on the side here. I get 2x squared plus 2x. And then when I plug in 1 for y, I get x squared plus 1/2 x. And then when I simplify this, I'll see 2x squared minus x squared is just x squared. 2x minus 1/2 x is 3/2 x. So that's all that is. So I'm just doing the integral from 0 to 2 of x squared plus 3/2 x. All right. And then I do the antiderivative of this with respect to x. So that is 1/3 x cubed plus 3/4 x squared, right? That looks right. From 0 to 2. So when I plug in 2, okay, I get 8/3 plus 3, right? Because the 4's cancel here. And then subtract the 0 is nothing. So it looks like it's 8/3 plus 9/3 is 17/3. Now we could have done this integral dz, dx, dy. That also would have worked, right? I could have started it by fixing a y and then integrating with respect to x going this way and then asking, okay, well, for each point in there, how high do I go in the z? But what has to happen is that z has to be the innermost in this problem, because z is the one that's determined as a function of x and y. That's what determines my height. And so we need z to be on the inside. And in fact, whatever has the most variable, whatever's determined in terms of the most variables has to be the thing on the innermost part. And the thing that is determined in terms of the fewest variables, in this case both x and y, they're just determined by numbers, can go on the outside. So the fewer the variables you're determined by, the further out in the integral you're going to appear.